Hello students, here we are going to learn about a new and a very interesting topic called as the linear block code. Okay, this topic is very important. Even from the exam point of view also, this topic is very important because most of the questions will be asked from this topic. Okay, and another important reason why this topic is very important is because the remaining portions that comes after this, the remaining topics that comes after this also depends on this particular topic, because this topic gives the basic foundation, the basic layout of coding, especially block codes, right? So that is why this topic is very important, and also it's very easy to understand. Also, there is not much to, there's not much for you to understand over here. Once if you grasp the concept very quickly, then everything that you can study from here that comes after this becomes very easy for you. Okay, so let's start with this. Okay, so here we are basically talking about linear block code. We all know what is a code, right? We all know what is coding. Coding is the transformation of a message into an encoded message, right? It's a transformation of a message into a code word. That is what is called as coding. So code or a code word is the transformed message. Okay, now what is the meaning of block code? Let's look at the meaning of the block code. In a block code, the information sequence is divided into input message block of k bits each. That is, k is the number of the input message bits. Okay, k is the number of the input message bits. That is the first letter you need to understand about this. Okay, in all the coming topics we will be representing k as the number of the input bits. Okay, so in a block code means we'll be taking an entire information sequence. If you have to transmit a sequence of bits, okay, if you want to transmit a sequence of ones and zeros, first before transmitting you divide that entire information into a block, into a fixed block of bits. Okay, and each of this block consists of k bits, and those blocks are called as the message blocks. Okay, those message blocks are represented by a binary k tuple. K tuple means k bits or k group. That's what a tuple means. So binary k tuple message called u. So each of this block, each of this message is represented by the letter u. So which means u is nothing but the input message. Just that's all. Okay, u is nothing but the input message block, and the length of u is k bits, or in other words, u is equal to u1, u2, u3 up to uk, where u1, u2, u3 are the bits of the message u. That is, the value of u1, u2, u3 and all are nothing but either it can be 1 or it can be 0. That is why it is called as binary k tuple. Okay, the u bit message is then transformed into an n tuple output encoded sequence. So n is the number of the output bits. Okay, n tuple output encoded sequence, and this n tuple output encoded sequence is represented by the letter v. Just like how we say that u represents the input message, v represents the output code or the output encoded sequence. Okay, and the length of v is n. That is, n is the number of bits of the output message or output code word or the output encoded sequence. N is the number of bits of the output. Okay, and the value of n is always greater than the value of k. That is, always the length of the output sequence is greater than the length of the input message. Always. Okay, so basically now we know what is a block code is, right? Block code means we are basically dividing the entire sequence into a number of blocks, and each block is consisting of k bits, and each of these blocks are converted into another sequence called as v, and the length of v is n. Okay, and the length of v is n bits, and this length is greater than your input message bits length. That is V is equal to V1, V2, V3 up to Vn. Okay. So U is called as the input message block or input vector. It's okay. We either use input message or we also use the word vector. Okay. And V is called as the output code word or code vector, or simply output code also we sometimes use the word, but this is more precise. V is called as the output code word, right? Each of these code words, that is every message is being converted into its corresponding code words. Okay. Since the input message will be k bit, then there will be a total of 2 raised to k messages, right? For example, if the input message is 2 bits, so if the input message is 2 bits, then totally how many messages will be there? 00, 01, 10, 11. So there will be 2 raised to 2, which is 4 bits, right? So if there's 2 bits, then there will be total of 2 raised to 2 equal to 4 bits. 4 messages. Okay. Likewise, if the input message is 3 bits, okay, if the input message is having 3 bits, then how many messages will be there totally? It will be 2 raised to 3, that is 8 messages. That is, what are those messages? It is 000, 001, 010, 011, 100, 101, 110 and 111. Like that, there will be 8 messages. Okay, so how many? So depending on the number of bits of the input messages, there will be 2 raised to k messages. And if each of these messages are converted to its corresponding code words, then there will also be a total of 2 raised to k code words. Okay, and since each message has its own code word, then there will also be a total of 2 raised to k code words, and each of these 2 raised to k code words is having length n bits. Okay, this is what you call as a block code. This entire explanation of what I said so far, okay, is what you call as a block code. So now you know what is a block code, right? The block code is that you convert the information sequence into a k bit message blocks, and each of these message blocks or each of these messages you convert it to another sequence called as V, where V is nothing but the code word and the length of this code word is n bits. Okay, and the value of n is greater than the value of k. That is the value of the code word bits. The number of the code word bits is greater than the number of the input bits. And since there and depending on the number of bits of the messages, we can say how many messages will be there. Depending on the number of bits of each message, we can say how many messages will be there. If the number of input bits is 4, then you can say that there will be 16 messages. And if there are 16 messages, then there will surely be 16 code words for each of these messages. That is, since each message has its own code word, then there will be a total of 2 raised to k code words of length n. Okay, so this is up to here is what you defined as the block code. Okay, but this is not simply just a block code. This is a linear block code. Now here comes the most interesting property about this chapter. That is, what is the meaning of the word linear? Okay. Linear, that is, a block code is said to be linear if it satisfies the following condition. So now let's see what the condition is. If V1 and V2 are any 2 code words of length n of the block code, then V1 XOR V2 is also a code word of length n of the same block code. What is the meaning of XOR? XOR means XOR can be thought of a binary addition, okay, but not simply an addition. It is a modular 2 addition. Modular 2 addition means there will be only 2 bits, right? 0 and 1, which means the answer should also be either 0 or 1. They cannot cross more than 1. Okay. The number that comes after 0 is 1, and the number that comes after 1 is 0. That is called as modular 2 counting, and the addition of that is called as modular 2 addition. For example, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1. And what is 1 plus 1? 1 plus 1, then it becomes next number. Next number is nothing but 0 itself. Okay, so therefore 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is 0. This is called as the modular 2 addition, also called as the XOR function, XOR gate we are using. We have learned about this in digital logic circuits, right? So this is basically an XOR function. So according to this property, it says that this block code is said to be linear if we choose any two code words from that block code. If you choose any two code words from that block code, and if you add these two or XOR these two code words, then the resulting code word is also one of the code word in that block code. The resulting code word is also one of that code word in that block code. That is the one of the most interesting property, one of the magic of this linear block code. Okay, we'll be seeing about this when you are doing an example. Okay, I will be using an example to explain all this. Okay, so this is what you call as a linear block code. Okay, so that means a linear block code means first you understand that it is each of these messages are divided into segments of blocks. And these blocks these input blocks or input messages are having k bits, and each of these messages are converted to an output code word, and each of these code words are having the length n, and they are called as linear because if you add any two of these code words, then the resulting sum is also one of the code word of the same block code. That is why it is called as linear. Okay, so therefore a block code that satisfies all the above properties, that is all the things that you have studied so far, a block code that satisfies all the above properties is called as, this is how we named it. We name it like this, that is we put a bracket and we say NK. This is called as NK linear block code, where N represents the number of output bits and K represents the number of input message bits. So this is called as NK linear block code. For example, if I say 7-4 linear block code, that means immediately you should understand that when I tell you the name 7-4 linear block code, it means the number of output bits is 7 and the number of input bits is 4. And if the number of input bits is 4, then there will be total of 2 raised to 4 is equal to 16 messages. And if you convert each of these messages into a code words, then there will be a total of 16 messages having 7 bits. Each of these there will be 16 code words, and each of these code words will be of 7 bits. That is called as 7-4 linear block code. If I use another number, for example, if I say 15-7 linear block code, 15-7 linear block code means then the number of output bits is 15 and the number of input bits is 7. So in that case, there will be a total of, since each message is 7 bit, there will be 2 raised to 7 messages. And since there are 2 raised to 7 messages, each of these messages has their own code word. So therefore there will be total of 2 raised to 7 code words, and each of these code words will be having a length of 15 bits. Okay, this property is called as the NK linear block code. Okay, I will be explaining all this using a problem so that you will be understanding very perfectly what it means. Okay, now we all know this property, right? That is, if you add any two code words, the sum is also one of the code word. So they're saying that if you add any two code words, if V1 or V2 or any two code words, so like I said, it's an XOR function, right? What is 0 plus 0? 0 plus 0 is 0. What is 1 plus 1? 1 plus 1 is also 0, right? According to this XOR function, 1 XOR 1 is also 0. So which means if V1 and V1 itself are being added together, you will get 0. Because if V1 and since it's an XOR function, if we XOR the two same code words, if you XOR two same code words, you will get the answer as all 0 code word, right? And according to this linearity property, if you add any two code words of the same block code, and then the resulting sum is also another code word of that same block. So which means if you add two same code words, then you will get an all 0 code word. And since according to the linearity property, adding of any two code words will result in this code word of the same block code. Then I can now say that this all zero code word is also one of the code word of an NK linear block code. That is what this message is saying. Since the sum of any two code words is also a code word, then the sum of the same code words, which is an all zero code word, should also be one of the code words of NK linear block code. This is what another interesting property about the NK linear block code. That is, if you add, according to this property, if you add any two code words of an input of an NK linear block code, if you add any two input code words, the resulting sum is also a code word. So because of that, because of this property is being satisfied, then definitely this property will also be satisfied, because according to this property, the sum of any two same code words, okay, the sum of any two same code words are being added, you will get all zero code word, because 0 XOR 0 is 0 and 1 XOR 1 is 0. So if you add any two same code words, you will get all zero code word, and this code word should also be one of the code word of the LK linear block code, so as to satisfy this property, linearity property. Okay, so therefore all zero code word will definitely be one of the code words, sure. Okay, that is one property of NK linear block code. Now how can I represent all these things what I have studied, what you have been describing over here? How can we describe all of this in terms of mathematics, or how can we express all of this on the paper? That is, we use it by using matrix. Okay, by representing each of these letters in the form of a matrix, we can express all this in terms of equations. If V and U, where V is the output code word and U is the input message, so if V and U can be represented as 1 by n and 1 by k dimensional matrices. What is 1 by n means? The 1 by n, that is, V is a matrix of dimension 1 by n. 1 by n means it has only one row and n columns, or one row and n elements. Okay, this since earlier is only one row and number of elements are there inside it. That is one row, and that likewise U is also can be represented as a matrix. So which means, and it's also having one row and k elements or k columns. Okay, so if we can represent these two in terms of these two matrices, then U can be transformed into V, that is, the input message can be transformed into a code word using the equation V is equal to U into G. This is very important equation, one of the basic fundamental equation of an NK linear block code. That is, the output message, you can get the output message using the equation is equal to input message multiplied with another matrix. Okay, now you will see what is this matrix is. So V is equal to U into G. Okay, so where G is an n by k dimensional matrix. G is an n by k dimensional matrix, that is, n represents the number of output bits and k represents the number of input bits, and n is also the number of, it's not n by k, it is k by n. It is k by n. Okay, I made a mistake. It is k by n. Okay, k by n. So that means here k represents the number of input bits and n represents the number of output bits. So k by n means k also represents the number of rows of the matrix G, of the G matrix, and n represents the number of columns of the matrix G. Okay, and that means we can represent the matrix G in this case. The reason is because only, how do I know this is? Because we all know about matrix multiplication, right? That means if this is of 1 by k, if this is 1 by k, let me write it. If this is 1 by k and this is k by n, okay. So if we multiply those two matrix, right, by matrix multiplication, you have studied this in school. If we multiply these two matrix in matrix, then the resulting matrix will be cancel the two the same value. These two should be the same value. That is, the column of one matrix should have the same number of the rows of the second matrix. So therefore, if we cancel these two, what do we get? If we cancel these two, what do we get? We get a 1 by n matrix. That is how I know it should be a k by n matrix. Okay, not n by k. It is k by n dimensional matrix, and this matrix is what you call as the generator matrix. This G is called as the generator matrix. Okay, we can represent this V using this sequence. So this sequence can be expanded in this form. That is, V is an 1 by n matrix. So this is 1 by n matrix, and U is a 1 by k matrix, which is, this is 1 by k matrix. See, 1 row and k columns, right? So this is a 1 by k matrix, and this is a k by n matrix called as the generator matrix G. That is, look how it is written: G11, G12, G13 up to G1n. This is the first row. The second row is G21, G22, G23 and G2n. This is the second row. Likewise, there will be third row is G31, G32, G33 up to G3n. That will be the third row. And like that, if you go down, there will be total of k rows. So therefore, the last row will be JK1, JK2, GK1, GK2, GK3 up to GKn. Okay. So therefore there will be k rows, and each of these rows are having n columns. This is called as the generator matrix. Okay, so this is how we transform the input message bits into an output code words. Okay, where the input message bits is having k bits, and the input message is having k bits, and the output code word is having n bits. This is how the transformation takes place. Okay, this is called as, this entire process is what you call as the NK linear block code. Okay, so now since we have now explained this much, okay, now let's do a problem so that I can now again try to make you understand each of these properties what I have explained so far. Okay, by doing a very simple problem. Okay, let's do this question. That is, look at this question. This is how most of the questions will be asked. That is, they will give you one of the matrix values and they will ask you to find the code words or any other problems that comes after that. Look at this question. A 6-3 linear block code has the following generator matrix. Now look at it. This is the generator matrix. That is, G is equal to 100011, 010101, 001110. So this is the generator matrix. Okay. So then they are saying it's a 6-3. Okay, as soon as when you know it is a 6-3 block code, you should understand that the input bits is 3 and the output bits is 6. So therefore, since the input bits is equal to 3, there will be 2 raised to 3 equal to 8 messages. So since there are 8 messages, there definitely will be 8 code words, and each of these code words are of 6 bits. Okay, immediately you should understand that. In some question, they won't even give you the name of the code word. They will not even give you the name. They just simply say a linear block code has the following generator matrix. In that case, how will I know the number of input bits and the output bits? The best way to know is simply look at the dimension of the G matrix. Okay, if you look at the G matrix has 3 rows. Okay, always the dimension is represented as k by n. So this matrix has 3 rows and 6 columns, so which means this dimension is 3 by 6. So if this dimension of the generator matrix is 3 by 6, then definitely this is a 6-3 block code. Okay, suppose I'm saying this, suppose if they have not mentioned the name of the block code also, there is no problem. You can simply understand which block code we are using simply by looking at the dimension of the G matrix. Okay, so this is the question: find all the code words. This is what I'm going to do. I'm going to find all the code words. So to find the output code words, they're asking us to find V. So to finding the output code words, you have to know what are the input messages. And what are those input messages? You see, since the number of input bits is 3, then the input messages are 000, 001, 010, 011, 100, 101, 110 and 111. Like that there are 8 messages. So we need to find the corresponding code words for each of these 8 messages. That is your question. Okay. So let's do this question. So we already know that this is a 63 block code. It will be V1, V2, V3, V4, V5, V6 is equal to, it's represented as U1, U2, U3 into the G matrix, which is 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0. Okay, that is, this is nothing but V is equal to U into G. That is why it's written like this. Okay, V is equal to U into G. This is V, this is U, and this is G. Okay, so now what I'm going to do is I'm going to substitute the value of the input messages. Since there are, this is the number of input messages are 000, 001, 010. So I'm going to substitute for each of these messages. I'm going to find the corresponding code word. Okay, so in that, when U is equal to 000, that is the first message. Okay, 00. If U is equal to 000, then what is V? Then V is equal to 000 into 100, 010, 001, 001, 101, 110. And what you get? You will surely get 0000000. This is the first message you get. Just simply multiply all this, you will get this message. Okay. Now when next message, when U is equal to 001, this is the second message. Okay, when U is equal to 001. So if U is equal to 001, what is the code word of this U? What is the code word of 001? Just simply multiply 001 with this 1 0 0 0 1 1 0 1 0 1 0 1 0 0 1 1 1 0. Okay, and the answer you will get is 0 0 1 1 1 0. Okay, how did I write this message very quickly? You see, you know how you do matrix multiplication, right? That is, you take this and you multiply it with corresponding columns, right? You take this row and you multiply it with every column, and that's how you got this. But I did not do that. I did not do this process. I simply looking at these two values, I simply wrote the final answer. What is the trick behind it? I will tell you how the trick is. The trick is simply like this. That is, since this is the third column, right? This is the third column. This is the first column. This is the first element. This is the second element. This is the third element. Okay, so this is the third element. That means the third element, only the third element is 1. If the third element is 1, then all you need to do is simply copy the third row. The third row will be the answer. That's what it means. See, very easy, right? Very easy. All you need to do is simply multiply this with every columns. You know that 0 into 0 is 0, 0 into 1 is 0, 1 into 0 is 0, and 1 into 1 is 1. So if you multiply this element, this row with every column, the first two rows will be multiplied with 0 itself, which will become 0, and only the third row will be multiplied with 1, which makes you get the final answer as the third row itself. That is how you got this answer. Okay, that's a trick. You can apply this trick anywhere. Now let's do the second. It is when V is equal to 0 1 0. Okay, when V is equal to 0 1 0. So in that case, so not V, I'm sorry, when U, the third message. Okay, the third message is 0 1 0. Okay, this is the third message. So in that case, what is the code word? Then v is equal to 0 1 0 into 1 0 0 0 1 0 0 0 1 0 1 1 1 0 1 1 1 0. Okay, and you will get it as this. Is here you can see the second element is 1, therefore simply copy the answer of the second row, that is 0 1 0 0 1 0 1 0 1. Okay, this is the code word of the third message. Now let's find the code word of the fourth message. When u is equal to 0 1 1. Okay, so then v is equal to 0 1 1 into, and over here is 1 0 0 0 1 0 0 0 1 0 1 1 1 0 1 1 1 0. Okay, so in that case you will get 0 1 1 0 1 1. How did I know this? You see, here in this case the second element and the third element is 1. So therefore, which means that since what we are basically doing is we are basically multiplying these two with every columns, right? And then after that, what we do is we add them together. So if you see the second element and the third element as 1, then what you need to do is simply add the second row and the third row. And when I say add, I don't mean the actual addition. I meant the modular 2 addition or the XOR function. That is 0 plus 0 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is 0. That function you need to apply here. So that's what I did. I basically XOR the second row and the third row to get this one. See, 0 plus 0 0, 0 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 1 is 0, 0 plus 1 is 1, and 1 plus 0 is 1. See, so quickly I did this addition. Okay, so I am saving a lot of time by doing that. So this is the fourth message. Now what is the fifth message? When u is equal to 1 0 0. Okay, when u is equal to 1 0 0. In that case, then v is equal to 1 0 0 into, and your generator matrix is 1 0 0 0 1 0 0 0 1. Here it will become 0 1 1 1 0 1 1 1 0. Okay, and here you will get the answer as, that is, this is the first, and only the first element is 1, which means simply copy the answer of the first row, which is 1 0 0 0 1 1. Okay, 1 0 0 0 1 1. Okay, this is the value. This is the fifth code word of the fifth message. Now let's look at the next one, that is when u is equal to 1 0 1. Okay, when u is equal to 1 0 1, then v is equal to 1 0 1 into 1 0 0 0 1 0 0 0 1 0 1 1 1 0 1 1 1 0. So here the first and the second element is 1, which means simply add the first and the third row. You will get 1 0 1 1 0 0. Right? Let me check. 1 plus 0. 1 plus 0 is 1, 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 1 is 1, 1 plus 1 is 0, and 1 plus 0 is 1. So there. This is the code word of the sixth message. Now let's write the code word of the seventh message. That is when u is equal to 1 1 0. Okay, when u is equal to 1 1 0, then v is equal to 1 1 0 into 1 0 0 0 1 0 0 0 1 0 1 1 1 0 1 1 1 0. And over here, since the first and the second element is 1, then simply add the first row and the second row, and you will get 1 1 0 1 1 0. Okay, this is what you get. Now when u is equal to 1 1 1. Okay, when u is equal to 1 1 1, then v is equal to 1 1 1 into 1 0 0 0 1 0 0 0 1 0 1 1 1 0 1 1 1 0. Okay, and here since all the elements are 1, which means you need to add all the rows. Okay, simply add all the rows using that basic XOR function, that's all. So 1 plus 0 is 1, 0 plus 1 plus 0 is 1, 0 plus 0 plus 1 is 1, 0 plus 1 plus 1 is 0, 1 plus 0 is 1, 1 plus 1 is 0, 1 plus 1 is 0, 0 plus 0 is 0. This is it. Okay, so these are the messages. Okay, so now what I'm going to do is I'm going to draw a table that on one side I will show all the input messages, and on the other side I will show all the corresponding output code words. Okay, so let me do that. So first I will I'll give the heading as input block or input messages. You can give any name you want, or you can give it input vector and output vector. That's also correct. So input messages. Okay, this is the input messages. And this is the output code words. Okay, so the input messages are U1, U2 and U3. Okay, these are the input message bits, and the output message bits are V1, V2, V3, V4, V5, V6. Okay, these are the output message bits or output code bits. Okay, then what are the different messages? The different messages are 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0 and 1 1 1. These are the different messages. Now I'm going to write the corresponding code words. Okay, and when the input message is 0 0 0, what is the output code word? The output code word is all zeros. Okay, 1 2 3 4 5 6. Now when the input message is 0 0 1, what is the output code word? It is 0 0 1 1 1 0, 0 0 1 1 1 0. And when the input message is 0 1 0, the output code word is 0 1 0 1 0 1. It is 0 1 0 1 0 1. When the input message is 0 1 1, when the input message is 0 1 1, then the output code word is 0 1 1 0 1 1. The output code word is 0 1 1 0 1 1. When the input message is 1 0 0, then the output code word is 1 0 0 0 1 1. When the input message is 1 0 1, then the output code word is 1 0 1 1 0 0. When the input message is 1 1 0, then the output code word is 1 1 0 1 1 0. And when the input message is 1 1 1, the output code word is 1 1 1 0 0 0. Okay, and there you have it. These are the input messages and these are the output code words. Okay, now I'm going to prove to you all the properties that I have taught you so far, so that you can now verify whether whatever I've said is right or wrong. Okay, what is the first property? I told you that this is a linear block code, right? So what is a linear block code? A linear block code, linearity means if V1 and V2, okay, if V1 V2 are any two code words, okay, if I'm choosing any two code words, okay, any two code words, and if I take the sum of those two code words or the XOR function of those two code words, then the resulting code word is also a code word of the same block code of length n. So choose any two code words. Okay, you can randomly choose any two code words, your own choice. Okay, I'm going to randomly choose a two code words. Which two code words should I take? Maybe I will take okay, let me take this code word and let me take this code word. Okay, I am going to take this code word and this code word and I am going to sum it. Okay, what is that code word? Let me see. The first code word here, this code word is 0 1 0 0 1 0 1 0 1. Okay, that is one code word. So let me just add it, 0 1 0 1 0 1. Okay, that is one code word. Now what's the other code word? 1 3 zeros 2 ones. 1 0 0 0 1 1. Okay, now I'm going to add it or XOR. Adding means XOR itself. So let me add it. It will become 1 1 0 1 1 0. Okay, so according to the linear block code, if you add any two or if you XOR any two code words, then the resulting code word is also one of the code word of the same block code. Let's see, is this 110 110 anywhere in your block code? Is it also one of the block code? See, is that block code exist anywhere? Let me see, what is the block code? 110 110, where it is? 110 110, where it is? There it is, there, here. See, 110 110, it's over here. That is, if I add two random different code words, I got a sum that is also one of the code word of the same block code. This is called as the linearity property. Okay, this is what you call as the linear block code. That is, if you choose, or you can choose any code word you want. That is what I'm trying to say. You can choose any code word, any two code words. If you choose, the resulting code word is also one of the code word inside the code. That is one of the beauty or one of the interesting property about this NK linear block code. Okay, and since if you are applying this property to the same code word itself, which means, since, like for example, what I meant to say is that, since, see, if I am choosing the second code word, okay, what is the second code word? 1 0 0 0 1 1. So this is a valid code, this is a valid code word, this is also a valid code word, and if you add these two valid code words, you will also get a valid code word. In the same way, this is a valid code word, and if you add the same valid code word with itself, if you try to find the sum of two same code words, you will definitely get an all zero code word. That is why an all zero code word should be one of the code word of an NK linear block code, which is true. If you check the first message code word, the code word of the first message, it is an all zero code word. So that is why it satisfies this property. That is, the linearity property also satisfies that there should be an all zero code word. Okay, this is what I was trying to tell you all this time. This is the understanding that I'm trying to give it to you. Okay, so I hope you have understood all this. Now let me tell you one more magic about this NK linear block, one more very interesting property, okay, about this linear block code. Okay, and that property is that it is about the generator matrix. If you simply look at the generator matrix, okay, if you simply look at the rows of the generator, let me take this example. Let me simply take this example, okay. If you take any one of the rows of the generator matrix, then each row of the generator matrix is also one of the code words. Each row of the generator matrix is also one of the code words of the NK linear block code. See, I can now you can see it for yourself. For example, let me see, what is the first row? 1 0 0 0 1 1. Okay, that is the first row. Let's see if this code word exists anywhere over here. It is which one? 1 3 zeros and 2 ones. Where it is? 1 3 zeros and 2 ones. This itself. See, this is actually the first row of the generator matrix. They are over here. 1 0 0 1 1. See, this is another important, very interesting property about NK linear block code. That is, one row, every row, each row of the generator matrix is also a code word. Look at the second row, 0 1 0 0 1 0 1 0 1 0 1 0 1 0 1. Where is this code word? Let me check. 0 1 0 1 0 1. They're over here. Oh, I do that also. See, 0 1 0 1 0 1. This is also a code word. That is the first row, the second row is also a code word. What about the third row? 0 0 1 1 1 0 0 0 1 1 1 0 0 0 1. There, over here, there, this one. See, 0 0 1 1 1 0. See, this is actually the third row This is actually the third row of your generator matrix. This is actually the second row of your generator matrix, and this is actually the first row of your generator matrix. See, so every row of the generator matrix is definitely is also the code word of that corresponding block code. If you are very smart, you will understand how that magic took place. It all took place because when you are trying to find the input message bits, you can see that only there will be a time comes where only one input bit of the message is actually 1 and the remaining bits are 0. Only when that time occurs only we will be getting the corresponding row. That is why those rows also becomes a valid code word in your linear block code. Okay, I just explained to you the trick behind the magic. That's why. Okay, so this is called as the NK linear block code. Okay, now one more small thing I need to make you understand about this NK linear block code is the weight of the block code. Weight. Let me name it as WEIGHT. Okay, weight of a code word. The weight of a code word is defined as the number of non-zero bits. Number of non-zero bits or non-zero bits is what you call as the number of non-zero bits in a code word is called as the weight of that code word. Okay, for example, over here the weight is 0 because all the bits are zeros. Here the weight is 3 because there are 3 non-zero bits. Here the weight is also 3. Here the weight is 4. Here the weight is 4. See, 1, 2, 3. So here the weight is 3. Sorry, here the weight is 3. Here the weight is how many in this code word? How many non-zero code bits are there? 1, 2, 3. So this is 3. Here there are 1, 2, 3, 4. Here there are 4. Here the weight is 4, and the weight of this code word is 3. Okay, this is called as the weight of the code words. Okay, this is called as the weight of the code words. And is the number of non-zero bits in the code word. Now let's talk about one more thing: the minimum weight of a code word. The minimum weight. That's also another interesting thing you can study. The minimum weight of a linear block code is defined as the minimum weight of all non-zero code words. The minimum weight in an NK linear block code, the minimum weight is the smallest weight of a non-zero code word, which means you cannot count this as a non-zero because here all code words are zeros. So the minimum weight should be the smallest weight of a non-zero code word. And what is the smallest weight? Here it is 3, right? The minimum value. Here the remaining, only except this one, the remaining are all non-zero code words, right? All 0 and non-zero. All 0 means all the bits are zeros. Okay, non-zero code word means some of the bits are non-zero, like the rest of them. Over here, the rest of them are non-zero code words. So here, the smallest non-zero code word is 3. So therefore, the minimum weight of this 6-3 block code is 3. Okay, there's one more interesting thing you can study. So basically, in NK linear block code, there are 3 basic interesting properties. The 3 important properties that you are going to study, you got to remember. If you want, you can write it down by yourself. The 3 interesting properties. That is, the first property is that if you add any 2 code words from this NK linear block code, the resulting sum is also a code word of that same block code. Okay, that is one property you have studied. The second property is that all 0 code word, that is 0, 0, 0, 0, 0, the all 0 code word should also be one of the code word of an NK linear block code. That is the second property. And the third interesting property is that if you look at the generator matrix, then each row of the generator matrix is also one of the code words of the NK linear block code. Okay, so these are the basic important properties of this block code. Hope you enjoy this video.